So which universe do we actually live in? And maybe more importantly, why this one? It's a question that keeps cosmologists up at night, and honestly, it's one of the biggest questions in all of science. Today, we're going to see if we can piece together the answer. The clues are out there, scattered across the cosmos, so let's start our investigation.
We're diving headfirst into two of the biggest mysteries you can think of. What's the recipe for our universe? What's it really made of? And what's its ultimate fate? Is it all going to collapse back in on itself one day? Or just expand forever into the cold and dark? Let me tell you, the answers are way, way stranger than you'd probably guess.
To figure this out, we're going to put on our detective hats. Seriously, we're going to follow three crucial pieces of evidence. These clues are spread across billions of years and billions of light years of space, but they all point to one single incredible and frankly very bizarre conclusion about the world we live in.
All right, our first clue takes us way, way back, all the way to the very beginning. And I'm not talking about the first few years, or even the first few seconds. We're going to the first few minutes after the Big Bang.
This period is known as Big Bang nucleosynthesis. It's a fancy name, but just think of it as a primordial furnace. The entire universe was this incredibly hot, dense soup of particles, and in those first moments, it was literally cooking up the first atomic nuclei. This was the universe's first real act of creation, forging the simple building blocks of everything that would come later.
Okay, now this graph might look a little intimidating, but the idea behind it is actually pretty simple. The theory predicts that the amount of light elements that got created, we're talking things like helium and deuterium, depends on just one thing: the density of normal matter. That's the stuff scientists call baryonic matter, which is just a fancy way of saying atoms, the stuff that makes you, me, the stars, everything we see. The curved lines on the graph show what the theory predicts. Now look at those narrow vertical bands. Those show what we've actually measured out there in the universe. See how they all cross the prediction lines in one very, very specific spot? That intersection, that is our clue. And what that little region tells us is honestly pretty shocking. It turns out that all the atoms in the entire cosmos, everything we can see and touch, only make up about 4% of all the stuff that's out there. Just 4%. So where is the other 96%? Let's file that question away for a minute and move on to our next clue.
So our second clue doesn't come from the first few minutes, but from a little bit later, around 380,000 years later, to be exact. It's like an echo from the infant universe, a fossilized picture of the cosmos right when it was first starting to clear up.
This is the cosmic microwave background, or CMB for short. It is the oldest light in the entire universe, and it's literally everywhere you look. And hidden inside the tiny, tiny temperature differences in this ancient light is the key to understanding the overall shape, the geometry of space-time itself.
So here's the deal. The overall shape of the universe affects how light travels through it. Think about it like this. If the universe were closed, sort of like the surface of a ball, those ancient hot and cold spots in the CMB would look bigger to us, magnified. If it were open, shaped more like a saddle, they'd look smaller, all shrunken. But if the universe is flat, they appear exactly the size they really are.
And this graph shows us the answer. The bottom axis shows the apparent size of those hot and cold spots in the sky, and the vertical axis shows how many of them there are at each size. The bumpy line is the actual data from our telescopes, and those dotted lines are the predictions for different shapes. See that first massive peak in the data? It lines up perfectly with the prediction for one specific geometry, at an angular size of about 1 degree. The evidence is overwhelming. Our universe is geometrically flat. Now, what that means is that the total density of all the matter and all the energy in the cosmos is at this very precise, critical density, just the right amount to stop it from collapsing back on itself or flying apart forever. But hang on, we already know from our first clue that normal matter is only 4% of that total. The mystery is definitely getting deeper.
Okay, on to our third and final clue. And this one came from looking at stars exploding billions of light years away. This discovery was such a shock to the system that it won the Nobel Prize, and it completely rewrote our understanding of the universe's ultimate fate.
The secret weapon for this discovery was a very special kind of explosion, called a Type Ia supernova. What's so special about them? Well, they all go off with the same predictable, unbelievable brightness. Because of that, we can use them as standard candles. It's like knowing exactly how bright a 100-watt light bulb is. If you see one way off in the distance, you can figure out exactly how far away it is just by measuring how dim it appears to be.
So back in the late 90s, two different teams of astronomers were plotting their data on a graph just like this one. The horizontal axis is how far away things are, and the vertical is brightness. Now, they fully expected their data points to fall along one of those lower dashed lines, which represent a universe where gravity is doing its job and slowing down the cosmic expansion. But look at where the actual data points are. The farthest supernovae are all consistently above those lines. They're dimmer, which means they're farther away than they should be. The universe wasn't slowing down at all.
In fact, the expansion is speeding up. Some kind of strange, repulsive force is pushing space-time itself apart, and it's winning the fight against gravity on the biggest scales. Scientists had no idea what it was, so they gave this mysterious pressure a name: dark energy.
Okay, so let's recap. We have our 3 clues. First, the amount of normal matter, which we got from the first few minutes after the Big Bang. Second, the flat geometry of the universe, which we learned from that cosmic echo, the CMB. And third, the accelerating expansion, revealed by those exploding stars. It's time to put it all together and reveal the true recipe of our universe.
And here it is. That 4% of normal matter we found with our first clue, that's us. That's everything we've ever seen or known. The accelerating expansion tells us that about 70% of the universe is made of this mysterious dark energy, and that leaves 26% for something called dark matter, some unknown substance that has gravity, that holds galaxies together, but that doesn't interact with light at all. This is our universe.
But here's the twist in our detective story. Just when we think we've solved the case of what the universe is made of, we stumble upon an even deeper mystery. A universe that is this precisely flat is just wildly, wildly improbable. On top of that, the cosmic microwave background is almost perfectly the same temperature in every direction we look. How is that even possible?
This diagram here really shows why that's such a huge problem. It's called the horizon problem. See those 2 cones coming from opposite sides of the CMB? Those cones represent all the information, all the light, all the heat that could have possibly traveled to that point since the beginning of time. And as you can see, their bases don't overlap at all. That means these 2 patches of the early universe were never in contact. They couldn't have exchanged heat to even out their temperatures. It would be like finding 2 people on opposite sides of the Earth who've never met but are somehow wearing the exact same, unique outfit down to the last thread. It just shouldn't happen.
So to solve these new, profound puzzles, the flatness and the uniformity, cosmologists came up with an idea so radical it sounds like science fiction. A new first chapter to our story. What if there was a bang before the Big Bang? This idea is called cosmic inflation, and it suggests that in the very first sliver of a second of its existence, the universe went through this period of absolutely unimaginable exponential growth. It expanded faster than the speed of light, which sounds impossible, but space-time itself can do that.
And this one idea, inflation, just elegantly solves our puzzles. It starts with a tiny, subatomic patch of space that was small enough to be connected and reach the same temperature all over. Then, in an instant, this inflation process stretches that tiny patch to be bigger than our entire observable universe. It's like taking a wrinkled-up balloon and blowing it up to the size of a city. From your perspective on the surface, any wrinkles or curves are stretched out so much that it looks perfectly flat.
So we have a picture that actually works. Inflation explains why the universe is so flat and uniform, and it sets the stage for the Big Bang we know and love. And that Big Bang then cooks up a universe filled with dark matter and dark energy. But what was the engine for inflation? What exotic, mysterious form of energy drove that initial violent expansion? That answer, for now, remains completely hidden in the dark, just waiting for the next generation of cosmic detectives to find the next clue.